Tesla. Tesla built pretty advanced electric vehicles. They introduced different services such as the Autopilot, automatic cruise control, lane assistant, and much more. But sometimes accidents happen. Here we can see a picture of an accident happened in Texas where media and research or people in general suggested that maybe the Autopilot was involved in the accident. So the Autopilot, which is one of the main services used in modern Tesla vehicles. But I think we can solve this case here and try to investigate the modern vehicle here, in our case the Tesla, and especially the Autopilot. So let's start and perform an investigation in automotive digital forensics, right? Before we start, we need to identify different digital evidence in modern vehicles. So usually we have infotainment systems installed. So mainly the main systems, which is somewhere in the middle of your main console at the front row in the vehicle. You have vehicle-to-vehicle systems, for example, for communication between vehicles, but also vehicle-to-X systems, which means vehicle to, for example, infrastructure. We usually have an airbag installed in modern vehicles. So we have the airbag control unit, which stores information some time before an accident, usually 5 seconds, and stores different information such as the vehicle speed and so on. We have the telematics control system, so for communication with the internet, especially usually with the back end of the OEM. With endpoint devices like smartphones, OBD dongles, and much more. So we now can see that we have a lot of digital evidence in modern vehicles. This also includes modern vehicles like Tesla vehicles. And in order to understand a lot, or at least try to understand everything in automotive digital forensics, we need some general understanding of the different components. This allows us to generate an overall picture of the digital events that have taken place in a specific time frame, so when the accident, for example, happened. And this also includes the Autopilot. This is why we want to focus on it right now in our case here. But before we start with investigating the Autopilot, especially, we should talk about what questions we want to answer. So what do we want to look at specifically? And there are some digital forensic questions we can answer. So one example is who performed or is responsible for a digital event. What was the digital event that was performed? When did a digital event take place? Where did the digital event take place? How the digital event take place? And last but not least, why did a specific digital event take place? When we are able to answer all those different digital forensic questions, we performed a very good and overall fully digital forensic investigation. But before we start trying to answer those questions, we need to take a step back and check what we actually want to focus on. As I've stated before, or at least we have identified before, we have different components, and one specific component which is interesting for Tesla vehicles is the Autopilot. But usually you don't have a specific location in a vehicle where logs are stored. This is very rare, so not similar to modern IT systems where you have something like this. This is pretty uncommon because we have a lot of different technologies, different data sources, which we need afterwards to correlate. But what is always there for all the different digital evidence we can collect from different systems, not only from vehicles, is metadata. And metadata is data that describes data. And what is pretty common here is that it is directly linked to a describing object. So it is specifically connected to an object that is described. So the metadata describes data for a specific object. For example, is the timestamp for a specific file or the object size for a specific file. Also the type of the file or the directory structure. So where is the file located in a file system? And for metadata, there are many, many more other examples. And you now might state the question, but why do we want to look at metadata? I said it before that usually metadata is always present, so we can always take a look at it. But we also have the benefit that metadata always changes when the object is modified, deleted, or otherwise changed. And this is pretty nice, because we don't need a third party or an external system like a CM to collect logs for us, and if it don't collect logs, we don't have anything to look at. We always have the metadata we can look at and try to answer the questions. And some previous research by Buchholz showed that metadata is able to answer forensic questions if the metadata is available. So this is pretty nice now, because we have talked about the different components in modern vehicles, identified the Autopilot as a relevant component in Tesla vehicles, and metadata as a pretty nice source to look at if we want to answer forensic questions. And this comes to our research question, which is what are digital forensics and automotive digital forensics specific characteristics that can be captured in the file system of a modern vehicle? And the corresponding hypothesis is that the file system of our Tesla Autopilot contains metadata that is relevant to answer forensic questions in an automotive digital forensic investigation. Awesome. So now we have our research question and the hypothesis we want to prove or disprove. But first we need to collect the file system we want to look at. In order to do this, we present here our approach, which is that we look at a Tesla vehicle, Tesla Model S from 2016, which has installed the Autopilot in hardware version 2. Currently, there is hardware version 3 on the market for all the new vehicles. Sadly, we were not able to look at hardware version 3 due to availability, but also usually hardware version 3 is encrypted, so you need a decryption key or an exploit in order to read it. We are pretty lucky because our hardware version 2 we collected was not encrypted, so we were able to analyze it. When we look at the component of an Autopilot ECU, so electronic control unit, we can perform a chip off to collect the data from the different storage devices on the component itself. This is what we did, and then we collected a SquasFS image. The image is pretty common for Linux systems. It's a read-only file system, which introduces a pretty similar structure to the most file systems you know from common IT Linux systems. So in order to analyze the system or the collected SquasFS, we performed two analyses, one with a custom Python tool we wrote, and next with a sophisticated digital forensic tool called Magnet Axiom. So let's jump straight into the results. We identified different extensions. Here you can see all the different extensions with the number of extensions found within the SquasFS. We can see that .so files, so linked files or shared libraries, are the most common, followed by .0, which are links. Certificates are pretty common too, such as configurations and image files, text files, or .bin files. Next, we take a look at the timestamps. The timestamps are pretty interesting too, because now we can see that at specific dates, specifically in 2019, we can see that a lot of files were committed to the SquasFS, which correlates that a lot of stuff has happened there. This is pretty common in the vehicle industry because unlike a smartphone or an IoT device, you need certifications and regulations to fulfill in order to get an approval from a safety authority. This means that you don't push minor updates and small updates out all the time for critical systems like the Autopilot. You perform this in a big bulk of files that need to be updated. So more user metadata that we collected from the SquasFS, here particularly using Magnet Axiom, for example, user accounts. It's root and daemon, which are pretty normal and common on Linux systems, but also we identified automotive-specific users. Here, for example, here are some examples like the temperature monitor, the visualizer, the legacy vehicle user, the driver monitor, or the GPS. This is all pretty interesting now because we can use this information in investigations, but also in other domains like pen testing to take a look, for example, for legacy vehicle. So why is this user there? Why is this relevant for the Autopilot? Some additional other metadata we identified is, for example, one CSV file, multiple PDF files, which are usually documentation files, 26 TXT files, most of the time those were READMEs, and 32 image files, which were pretty interesting because those are the firmware images for the different services like the Autopilot itself or Hermes, which is used to communicate with the backend. And we also identified the build root configuration with a unique identifier here. The build root is a Linux tool used to create a Linux image, usually embedded images. In this case, Tesla used build root, which is pretty awesome in my opinion. So now I've presented a lot of different metadata we collected, but this raises one question. Can we trust the data? Well, when we talk about trustworthiness about data, you usually talk about forensic soundness. And forensic soundness is the degree of correctness, atomicity, and integrity in memory acquisition. This correlates to, was the data changed while acquiring it? Is the stuff you collected actually the stuff that was written in the memory? Have you collected the correct memory regions, and so on and so forth? And due to the fact that we performed a chip-off, so embedded forensic technique, we are forensically sound. Because when you perform a chip-off, you quote-unquote freeze the image and then you collect it. This leads to fully forensic soundness to a high degree, and we are forensically sound, which is pretty awesome. But the next question that arises is, how helpful is actually the data we collected? Here we can see a list of, or a table of the forensic questions and the corresponding identified metadata. So to answer who, we can use the user accounts or cron jobs we identified. To answer where, we can see the files and the folders structure itself. So where was something located, for example, where could you find a specific piece of malware if malware was deployed in a security incident involving a car. When we can look at the different timestamps of the files, but also we have some log files for some systems or some services like Hermes. What also includes the log files, specifically within the etc folder. There are a lot of log files installed for all the different tools running within the Autopilot. How directly corresponds to the configuration files we found, so .rules files, .conf files for the firewalls, for IP tables, and so on, which are pretty interesting in future investigations too. And last but not least, why this was not answerable using the metadata, because the metadata does not have an opinion on the data. It just states the facts which are there, so we cannot prove why some digital event occurred. This is not part of the metadata we collected. So awesome. So we were able to answer the questions. So let's go back to the beginning of the talk. Let's summarize everything. We had the reset question, what digital forensics and automotive digital forensic specific characteristic we can identify it in a file system. And we identified general characteristics like common usernames used, or common services used, or common file structure from a Linux system, but also automotive specific characteristics like the users we have seen, the legacy vehicle one, GPS, temperature monitor, and so on. And the hypothesis was that the file system of a Tesla Autopilot contains metadata which is relevant in automotive digital forensic investigations. And this is also correct because we can answer nearly all questions, all forensic questions stated or required in digital forensic investigations, except of the why. So that's pretty awesome. Now we have shown that we can use the Autopilot image or images from the Tesla Autopilot in future investigations, which is awesome. Thank you very much for your interest in the talk, and I'm happy to answer questions.